All right, let's start talking about chapter 19, which personally I think is one of the most important chapters in the book and topics that we cover simply because it is the most practical for most people who take chemistry. Things in your real life you will come across more often talking about acids or bases than many of the other chapters. All right, again, as usual, take a look at the vocabulary and make sure you can answer those or define those, I should say, as we move through the chapter. Let's take a look at the opening question. It says, where do you think the idea of calling substances acids and bases began? Just a very brief history. Before science was an actual science, we had what we call alchemy. And alchemy was basically people mixing compounds they found in nature together to do one of two things: convince people that they could turn, say, lead into gold, and they developed potions that they called the elixir of life. In other words, it gave you mortality. It gave you immortality. So basically, they were shysters. But they were mixing actual compounds together and getting chemical reactions. So anyway, when people started eating food and using things that they found in nature for practical purposes, what they found was some of these things tasted tart or sour. Some of the things tasted bitter. So they started classifying these things. If plant A, B, and C all tasted sour or tart, they put them into one category, and if things tasted bitter, they put them into another category. So anyway, these categories started to become known as acids and bases. There are three basic types of classifications of acids and bases, and we're going to start with the first one, referred to as Arrhenius acids and bases. So let's take a look at acids first. As we said, acids have a tart taste or a sour taste. Lemons would be a good example of that. The acid, or I should say the compound in lemons, is called citric acid. That's another thing. We're going to name a number of common compounds in the formulas, or I should say the chemical names for those common compounds, and there are a handful of them that I would like you to know. Acids produce strong and weak electrolytes. And if you remember back a ways, an electrolyte is something that if you put it in solution, it breaks apart and forms a positive ion, which we call a cation, and a negative ion, which we call an anion. So in solution, those positives and negatives can conduct electricity. So that's what makes something an electrolyte. If something breaks apart 100%, we call it a strong electrolyte. And if it breaks apart less than 100%, we called it a weak electrolyte. So acids break apart and form those positive and negative ions. Car batteries would be an example of a strong electrolyte. Most car batteries, the chemical is sulfuric acid, and we'll talk about that a little bit later. Acids react with indicators to change color, and we'll talk later about what indicators are. Bases, as we said, have a bitter taste. Bases feel slippery. Most soaps are made out of some sort of base. One of the common compounds used in soaps is sodium hydroxide. It's also the compound that we call lye. And we'll talk a little bit later about what that is. Bases also produce strong and weak electrolytes, and bases also react with indicators to change color. All right, let's talk a little bit about the history of Arrhenius. Arrhenius, around 1887, his first name was Savante, came up with the definition of an acid and base. In other words, we couldn't just scientifically say, hey, there are things that are sour and things that are bitter. We need a chemical definition. You don't have to memorize dates, but I do like you to have an idea of when things happened. And I always base things on the year 1776, the year our nation was started. Around 1760 to 1840, the Industrial Revolution. In other words, we started building factories and making things. A very important time in this country. The late 1800s are when science and technology really started to take off. And a lot of these things that we've talked about this year started taking place in the late 1800s. So, just to give you an idea of when these things happen. All right, Arrhenius described an acid as a hydrogen containing compound that produces the H plus ion in aqueous solution. So, for example, let's take a look at hydrochloric acid. If you have hydrochloric acid in aqueous solution, it means you put it into a beaker of water, and what happens is those H pluses and Cl minuses break apart. So hydrochloric acid breaks apart in aqueous solution to form the hydrogen ion. That is what makes it an acid according to Arrhenius. So it is ionizable. It forms ions in solution. Monoprotic, mono meaning one, protic meaning the hydrogen ion. If you remember back, hydrogen contains one proton and one electron. So if we remove that electron and make it a positively charged ion, the only thing that's left is a proton. So we call it monoprotic. Basically, what it means is it contains one hydrogen. All right, let's take a look at sulfuric acid, which is H2SO4. It's diprotic, two hydrogens, and it's going to do two things really. It's going to lose that hydrogen. Now it's not going to be SO4 since there's two hydrogens, we still have one left, and that's going to be the polyatomic hydrogen sulfate. So H2SO4 dissociates or ionizes, forms the H plus ion and that polyatomic. Now that polyatomic can also undergo an ionization, lose its hydrogen, and now we have the sulfate polyatomic. And that's a little bit special case, and we'll talk about that maybe. I don't know if we'll get that far this year, but that's a special case. What you need to know when we talk about sulfuric acid dissociating, we're using this dissociation reaction. It's referred to as the first dissociation. It gets rid of one hydrogen, and then you have that polyatomic left. Phosphoric acid, triprotic, three hydrogens. It's going to do the same thing. It's going to get rid of that first hydrogen. Now it's got two left with the 1 minus charge. Now that polyatomic can undergo its own ionization, and then it can undergo one more since there's three. But when we have what we call polyprotic acids, in other words, more than one hydrogen, we're always going to assume one dissociation. All right, we're going to stop there. I'm really trying to keep these videos under 10 minutes each and cover shorter topic, or I should say, cover smaller bits of information, but talk about them in a little bit more detail. So we're going to stop there, and then we will pick up in the next video.